Hello everyone, I'm Tanya. I'm one of the TAs assigned to the course Aircraft Stability and Control taught by Professor A.K. Ghosh. So we will go over the contents of week 10. Before that, we'll solve a few questions of week 9, going over the main points that will help us solve the questions. So let's begin. Okay, so what we had studied so far was static stability. What is static stability? It is the ability of any body to get back to its equilibrium position. It is the tendency to get back to its equilibrium position when it's disturbed. For an aircraft, we had gone in detail for the longitudinal, lateral, and directional stability, and we had seen three conditions that tell us if the aircraft is stable or not. So for the longitudinal case, the only condition was that Cm alpha should be less than 0. Okay, which is this condition here. Cm alpha must be less than 0. The only condition for longitudinal static stability. What is the structure of an aircraft that contributes towards this? It's the horizontal tail. Okay, so horizontal tail is what gives you an inherent ability to come back to its equilibrium position when it's disturbed in the longitudinal sense. For the lateral case, the only condition that we require is that C and beta should be greater than 0. This one. Alright. So what is the structure that contributes towards this? Vertical tail. Okay. Then for your directional case, you have CL beta should be less than 0. So these are the only three conditions required for static stability: longitudinal, directional, and lateral. Okay. Alright, so the structures that contribute towards lateral stability are vertical tail, high wing, and dihedral. So if you have a low wing, it should have a dihedral angle. What is a dihedral angle? So this is a low wing, and if you introduce a dihedral angle, it will look something like this. And enhedral is something that is opposite, something like this. Alright, okay. Then we moved into dynamic stability. We looked at the equations of dynamic stability. So these were the equations that pertain to dynamic stability of a point mass in 2D. In 2D. Okay, so for a point mass body in a 2D, two-dimensional scenario. So we have four equations of motion. One that tells you V dot, how V dot changes. The other one tells you how gamma dot changes. Then you have your translational cases. That is X dot and Y dot. Okay, so this is for a point mass case. Now let's look at the dynamic stability for an aircraft. Okay, in the longitudinal sense. So in the longitudinal sense, we know for the force we have CL, for the moment we have Cm, where Cm is the pitching moment coefficient. Okay, so till now, what were the linearized equations for these two coefficients that we saw? So CL was CL naught plus CL alpha into alpha plus CLQ. Okay, this was not there. Let me just erase this. So initially it was just these two, CL naught plus CL alpha into alpha. Then when we came into controls, we had CL delta E into delta E. Just give me a moment. Alright, so then we saw the pitching moment coefficients, right? So pitching moment coefficient again. Oh, let's just complete this. So when the control came into the picture, your CL delta E into delta E came into play. Alright, now when the dynamic stability comes into play, you have two new terms that come into this linearized equations of the stability derivatives. Okay, so you have two new parameters, which is Q and alpha dot. Q and alpha dot. Q is the pitch rate and alpha dot is the rate of change of angle of attack. Okay, so these two terms come into play only when do they come into play? When do they come into play? Only when the aspect of time comes, right? So till now we were not dealing anything with time. It was just static stability. When the dynamic stability comes, we have two new terms, that is Q and alpha dot. So ideally, if you're going according to the same expansion, what, just a minute. Yeah. What we should have got is, we should have got a CLQ into Q. But you can see the term here is different. Why is it different? We had dealt with this extensively before. Can you tell me why it's different? Can anyone tell me why you have CLQ into QC by 2V? Also CL alpha dot into alpha dot C by 2V. Why? Why is there a difference? Why is there a difference? Why can't it just be CLQ into Q? See all the other terms, so CL, what is the dimension of the CL? What is the dimension of CL? Can someone tell me what is the dimension of CL? CL naught. CL alpha, what is the dimension of CL alpha? Start with each of those. CL dimension. What is the dimension of CL? It is dimensionless. Less. What about CL alpha? What is CL alpha? It is dCl by d alpha. Okay, so what do you think would be the dimension here? CL is dimensionless, so dCl by d alpha, it's a dimension of alpha. So this would be per radian, correct? So now this entire term thus becomes dimensionless. So in order to make the CLQ in that term also dimensionless, you take QC by 2V. Q, what is the dimension of Q? Picture it Q or alpha dot. Radian per second. Okay, so if it was just CLQ into Q, that term would not be dimensionless. You will have a per second there, right? So we have defined this QC by 2V. So it's just the 2, that denominator 2, I think someone asked this in the forum. The denominator 2 is just a term, just R notation, just R nomenclature, okay? So you can do away with that 2, but just make sure that you maintain the same notation throughout, okay? So now tell me how CLQ is defined. How is CLQ defined? We know that it's multiplied by QC by 2V. So how is CLQ defined? That 2 is just your convention, okay? Just our convention. It could very well be QC by V. Then also it will be dimensionless. So the QC by 2V is just our convention. Okay, now tell me what is CLQ. The derivative CLQ, how is it defined? Like CL alpha was dCl by d alpha. So what is CLQ? dCl by, I think we'd seen a question, or there was a question even in your assignment, I believe, and we'd even seen a question last lecture, last session. You don't need to do all that. Just look at that term CLQ into QC by 2V. If that has to be non-dimensional, how is CLQ defined? DCL by DQC by 2V, right? Correct. So that's how it's defined. Similarly, how is CL alpha dot defined? How is CL alpha dot defined? Similar, it's very similar to the Q case. DCL by D alpha dot. Correct? Similarly, for your pitching moment coefficient, you have initially you had only Cm naught plus Cm alpha into alpha. Then when your control came, this term came into play, and now two new terms when the dynamic stability is coming into play. You have CMQ and Cm alpha dot, which are defined in similar ways like CLQ and CL alpha dot. Okay. Now, due to this pitch rate Q, there is a change in angle of attack, delta alpha. So that is given here. Now, because of the pitch rate Q, you have change in angle of attack. So if there is an increase of angle of attack at the tail, will the lift at the tail increase or decrease? So this is your tail and its angle of attack is increasing. You have delta alpha. Okay, at the tail. This is at the tail. So will your lift at the tail increase or decrease? It will increase. You have delta L, that is given by this equation. Now when the lift at the tail increases, it will produce some moment at the CG, it will some change in moment at the CG. Will it be positive or negative? According to our convention, let me just do this. Pitch down, positive or negative? According to our convention, pitch down. Pitch down is negative. So, due to an increase in lift at the tail, will it produce a pitch down or pitch up motion? It will produce a pitch down, which is why you have this negative sign here. Okay, do not get confused why the negative sign came. Is because the increase in lift of the tail produces a pitch down moment. Okay, that is why you have a negative sign there. Let me just write that properly. Okay, which is why you have this negative sign. Alright. Then we had seen this even in the last session, how the equation is related to a spring mass damper system. Okay, so here your stiffness K is akin to your Cm alpha. Right? Stiffness coefficient K is similar to your Cm alpha. It is the, what is Cm alpha? How did you define Cm alpha? How did you define Cm? What was Cm alpha? DCm by d alpha. For stability, it should have been less than 0, right? So Cm alpha is the term that withstands any perturbation, tends to withstand perturbation, right? So it's that stiffness, it's the obstruction towards the perturbation, it's the resistance offered towards perturbation. Okay, so that is your stiffness parameter. Next derivative is your CMQ, which is related to your damping coefficient. CMQ comes into play when dynamic stability comes, that is when the aspect of time comes. So over time, will the body attain equilibrium? Will it come back to equilibrium? Will it go away from equilibrium? Or will it attain a new point to as equilibrium? That is what your CMQ tells you, which is what your damping coefficient also tells you. That is, over time, once it's disturbed, will it keep oscillating about the equilibrium point? Will it deviate further away from equilibrium point, or will it oscillate and come back to equilibrium point? Okay, so this is what both your damping coefficient and your CMQ, both of them tell you. Okay. Then we saw the forces that we have taken into consideration. We have three kinds of forces: aerodynamic, gravitational, and propulsive. What were the aerodynamic forces? I remember asking this in the last session as well, and none of you replied. What are the aerodynamic forces that we have taken into consideration throughout this course? Lift and drag. They depend on the relative velocity. Gravitational force, the weight, and the propulsive force is the thrust. Okay. Then you have two frames defined here: the inertial and the body. Okay. And then there was this relation that we had seen in the last session. That was the relationship between a derivative in the inertial frame and the body frame. I think we will derive that again this time, because it's very important for not just for this course, but for any dynamical analysis. You need this. Why? Because your Newton's laws of motion are only valid in the inertial frame. But it so happens that there are several times it's easy for us to measure things in the body frame. So we need a relationship between the body frame and the inertial frame. Now here, of these three categories of forces, what all do you think are measured in the body frame, what all are measured in the inertial frame? Not just the forces, just take the other parameters. So here you have all the parameters. You have force, velocity, angular velocity, moment, angular momentum. Yeah. So tell me what all are measured in the body frame, what all are measured in the inertial frame. Just take a moment, go over it, tell me what all are measured, write it down, and tell me what all are measured in the body frame, what all are measured in the inertial frame. We need to justify why we have this relationship, right? So this is called the Reynolds transport theorem, this one, which gives the relationship between derivatives in the body and the inertial frame. Can anyone define how inertial and body frame are defined, or give me the difference between them? Let's actually start with that. Can you tell me the difference between the inertial and the body frames? Anyone? We'll discuss this. Google it, look it up, look up your notes, look it up and tell me. I'll give you a couple of minutes, look it up and tell me. Have you been able to find out the difference between inertial and body frame? I don't think I am going to tell you the difference now. You need to know this. Look it up. Okay. Now tell me what all are measured in the inertial frame and the body frame. You should know the difference between the inertial and the body frame. Now tell me what all are measured in the inertial frame and what are measured in the body frame of the parameters given in these equations. The forces, the velocity, the momentum, what all? Give three categories of forces. What all are measured in inertial? What all are measured in body? Are they all measured in body? Are they all measured in inertial? Aerodynamic forces, lift and drag, they're measured in body frame or inertial frame? Lift and drag measured in body frame or inertial frame? Okay, you will look up this and tell me in the next session. So what all are measured in the inertial, what all are measured in the body frame. Now let's try and do the derivation for this Reynolds transfer theorem. We've done this in the last session, so like guide me through this. Okay, so I'll define two vectors. So a vector in the inertial frame, ax I plus ayj plus azk. Okay, and the same a vector in the body frame, axi plus ayj plus azk. Now let's take the derivative in the inertial frame. So dA by dt is dAx by dt I cap plus dAy by dt j cap plus dAz by dt k cap. Then you have, using chain rule, Ax d I cap by dt plus Ay dj cap by dt plus Az dk cap by dt. This was in the inertial frame. Okay, now tell me if this equation is right. Ijk are capital here. Okay, I made a mistake there. Ijk are capital. Now tell me if this equation is right. The last three terms are 0. Why are the last three terms 0? So the last three terms are 0 because the rate of change of I, j, k are 0. Why? Because the inertial frame is fixed, right? So we have defined our inertial frame such that it is fixed. What is the inertial frame? Now do you understand the difference between inertial and body? So inertial frame is fixed in time. So di by the unit vectors defining the inertial frame are fixed in time. Okay, so di by dt, dj by dt, dk by dt are all 0. So the differentiation of the vector in the inertial frame is just the first three terms. Okay, now let's take the derivative in the body frame. Derivative of the same vector. All of this should have been capital. Let me just write that again. Just give me a minute. All of those should have been capital because we're taking the derivative in the inertial frame. So we've defined our inertial frame using capital letters. These three are 0. Okay. Now let's take the derivative in the body frame. Here you have dx by dt Okay. Now is this right? The second equation, derivative of the same vector in the body frame, is this right? Is it right? Do any of the terms go to 0 just like the inertial derivative case? No, they don't, because your body frame is not fixed in time. Okay, so the unit vectors move with the body. The unit vectors are fixed on the body, and when the body moves in time, the unit vectors of the body frame also move. So d small I by dt, d small j by dt, d small k by dt, they are not 0. Okay, so you cannot equate them to 0 like the inertial unit vectors. Okay, so now when a body is rotating in time with an angular velocity omega, the rate of change of unit vectors is given by, so if this is represented by, let's say, how do I write it? Okay, di by dt is omega cross I. Okay, if the vector I is rotating with the angular velocity of omega, then its derivative is given by omega cross I. So when you substitute this into the above equation, what you get is, it equates to dA by dt body frame, which is these three terms, and the second three terms, or the ones in the second line, give you omega cross A. Okay, is that clear? They give you omega cross A. So what we understand is that dA by dt in the inertial frame is equal to dA by dt in the body frame plus omega cross A. Is this clear? Which is what is your transport theorem. Now using this equation, we can write the force and the moment equations given here. Correct? So this is the body frame and this is the omega cross Vc. This is again the body frame, this is omega cross, okay, here there should not be an M. This is omega cross H. Okay? So this is where we use this transport theorem, because we measure some quantities in the body frame and some quantities in the inertial frame, which you will be telling me in the next session. Okay. We've already gone over the different parameters, the force, moment, velocity, angular moment, angular momentum, all of that. Okay. Now the dynamic stability. Why aren't the slides changing? Are the slides changing for you? Alright. So now we take these three equations, the force and the moment equations, expanded it. From where did we get these equations? From the two, the force, this force equation and this moment equation. Okay, so each of those are three equations. So together we get these 6 equations of motion for an aircraft. Okay, let me turn off the video because it's lagging here. Alright, so you get these 6 equations of motion. That describe the motion of an aircraft. Okay, so Fx, Fy, Fz, L, M, N. Okay. So here you can see that the force is split into 3 terms, that is Fa, Ft, Fg, where A is the aerodynamic forces, T is the propulsive forces, G is the gravitational force. Okay. Then we studied something known as the Euler angles, psi, theta, phi, and like I had mentioned in the last session, the psi and theta are not to be confused with the yaw and pitch. Okay, these are the inertial, the orientation of the body frame with respect to the inertial axis. Okay, whereas your yaw and pitch are in the body frame, right? They are measured with respect to the body frame. Okay, they are different from these Euler angles. Now, where do these Euler angles come into play? They come into play in 2 places. One is the gravitational forces and the other is this PQR, that is omega. Okay, so the Euler angles and the rate of change of the Euler angles come into play in this PQR, which is omega, and the Euler angles as such come into play in the gravitational forces. Now here you can see that the theta and phi are present. Why is psi not present? First of all, let me tell you why these Euler angles are coming into play in the gravitational forces. So I had asked you to come up with this in the next session, but anyway, it's okay. So the gravitational forces are measured in the inertial axis. When we convert them to the body frame, we rotate it using the Euler angles. Okay, so that is why these theta, phi terms are coming into the gravitational forces. Now, can anyone tell me why xi is not coming? You only have theta and phi. Xi is not there. Why? Why is xi not present? Can anyone tell me? Why is the angle xi not present in these gravitational equations? How is this xi defined? It is not the yaw angle. How is xi defined? Someone tell me that. What is xi? It's written there. It's about the ZE axis, where ZE is the inertial axis. So, how is xi defined? What is xi? How is xi defined and why is it not there in the gravitational forces? Why is xi not? Just take a moment, look at it, look at the equations, look at how we have defined it, look at the axis, look at the aircraft axis. So how is the weight of the aircraft, along which axis is the weight of the aircraft? It's along the z axis, right? So why should the orientation of the z axis come into play? Correct? That is why xi is not coming into play. Is that clear? The weight of the aircraft is along, so if this is your aircraft and this is your xb, this is your yb and this is your zb, the weight of the aircraft is always acting vertically downward. Correct? It's not acting along ZB, that was a mistake, but it's always acting vertically downward. So it will always be along that inertial Z axis. Correct? Either positive or negative, but it will be along that Z axis. So the orientation xi of the aircraft with respect to inertial frame will not come into play when the weight of the aircraft is measured. Does that make sense? Yes? Okay, let's go ahead. Okay, now let's look at the questions of week 9. The transformation sequence used for body fixed frame to inertial frame to derive the 6 degree of freedom equations of motion is. We just discussed this. What is the standard rotation sequence for body fixed frame to inertial reference frame? Is it 331, 313, 321 or 312? Where 3 is about the z-axis, 2 is about the y-axis and 1 is about the x-axis. So which is it? This is the conventional rotation sequence that we follow. Is it 321? Is it 312? Is it 313 or 331? It is 321. Okay, it's always in that sequence. Okay, now the next question. The rotation matrix for wind axis system to body axis transformation. Wind axis. When do we use the wind axis? The wind axis is for the relative velocity. What is it also called? When do we use this? You can see that the angles alpha and beta come into play here because of the wind axis. Otherwise it will be phi theta psi. Now you have alpha and beta. I believe I had a question regarding this. Just give me a minute. Can you see this aircraft? Yeah. Can you see this aircraft? So this is where the alpha and beta come into play. Here only alpha is seen, but where does the wind axis come into play? Can someone tell me? Wind axis is also known as the stability axis. Okay, so we use the wind axis or the stability axis to simplify our equations of motion. Okay, there is a slight lag in. Okay, yeah. So there is the wind axis or the stability axis are used to simplify your equations of motion, because if we take our forces along the direction of motion, along the direction of the wind, then lot of these sine cos terms are not needed to, they will not appear in the equations. The equations are greatly simplified. That is where we use these wind axis or stability axis. Okay, so how do you rotate from wind axis system to body axis system? What is the sequence? The first matrix is same, right? The first matrix is rotation about x-axis, about an angle phi. So this is rx phi. This is constant. All right. Now you just have to concentrate about the other two axes. That is about what axis do you rotate alpha, about what axis do you rotate beta. And if you look at the equations carefully, you get it. So it will be ry alpha and rz beta. So all you have to see is that you rotate with the primary matrices. Alright, so you just have to, so primary rotation about x-axis is given by what matrix? Rotation about y-axis, rotation about z-axis. So which of these four options is right? Just look at the primary rotation matrices. Which is it? It's the first option, right? The primary rotation matrix about y-axis is cos 0 minus sine 0 1 0 sine 0 cos. The primary rotation about z-axis is cos minus sine 0 sine cos 0 0 0 1, which is the first option. You must remember the primary rotation matrices about each axis, okay? So they will be greatly helpful. I think one of the questions that we saw in the previous session, where we had to multiply these three matrices, there also you'll only get the right answer if you know the three matrices. Alright? Okay. Now let's look at the next question. For general trim flight, which condition is true for Euler rates? Phi dot, theta dot, psi dot. Which condition is true for trim flight? What was the trim condition? Sir had dealt with this explicitly in the lectures. He had in fact told this very condition. For trim, what are the only two conditions required as far as Euler rates are considered? For trim, are all three 0 or none of them 0 or a combination? only two rates are 0. Only two rates need to be 0. So which are those two rates for general trim? You had all done this assignment, right? So just tell me. It's the first one, right? Only phi dot and theta dot need to be 0. Psi dot may or may not be 0. Correct? So this is the general condition for general trim. Okay. During the process of determining Euler angles, the rotation xi about x-axis is defined as. Yes. So now they've asked you for the primary rotation matrix about the x-axis, where the angle is xi. The angle can be anything, you just need to know the primary rotation matrix about each axis. In this case, they've asked you about the x-axis. So which one is it? If it's rotation about the x-axis, the first element will be 1, right? So the first row and first column will be 1 0 0 1 0 0. Correct? So this is something that you can remember. If it's about y-axis, the second row, second column will be 0 1 0 and combination of that. If it's about the z-axis, the last row will be 0 0 1 0 0 1. Last row, last column. Okay, so it's one of these two options. Now, what is the correct sequence for cos and sine? We've just seen these matrices in the previous case. So this is the correct rotation matrix of the x-axis. So you can see here, which was x. Yes, this was x. Correct? Okay. Just correct me if I'm going wrong anywhere, okay? From the above question, what is the value of Rxi into Rxi transpose? Where Rxi is okay. What would it be? Rx is the rotation matrix. So Rx into Rx transpose will be. How do you define a rotation matrix? It's one of the properties of the rotation matrices. Rx into Rx transpose will be. Rx into Rx transpose will be. Just multiply the two matrices. Now you have the matrix, just multiply it and see. Or take any primary matrix, primary rotation matrix, and multiply it with the transpose. Just do it. I'll give you a couple of minutes. Just take this matrix that you have here and multiply it with its transpose and tell me what is the value. give you a couple of minutes to do this. Just multiply and tell me what is the value. Did you multiply the rotation matrices? What is the value that you're getting when you multiply with its transpose? You're getting an identity matrix, right? So this is the property of all rotation matrices. The matrix into its transpose will be an identity matrix. Okay. Okay. Now let's move on. Okay. So these are some additional questions. The gravitational force components along the x, y, z axis are respectively can be written as in terms of the Euler angles. Okay. It's taking some time to load. Okay. Yeah. So now you can see the question. So this is a direct question, you know the values. Just tell me which one is the right option. Refer to your notes. The previous slides in fact had these values. So these were the Fx, Fy, Fz components of the gravitational force, right? So now tell me which one is the right answer. It's a direct, I've given you the values. Which is the right answer? Fx is minus mg sine theta, then you have mg cos theta sine theta, and then you have mg cos theta cos theta cos phi. It's this one, right? Okay. Now this is the figure that I had shown you previously. It's taking some time to load. Okay. In the following figure, xb, yb, zb are the three axes of the aircraft body frame. xi, yi, zi are the axes of the inertial frame. X dash, y dash, z, x dash, y dash, z dash, actually z dash are the three axes of the intermediate frame, and v is the velocity vector. Which of these three constitute the stability axis? Just a minute. Stability axis was the wind axis, right? Why did we choose such an axis? Because it will greatly simplify our equations of motion. Right, so if it is a wind axis, what is the stability axis here? The velocity vector is given by v. So v, anything aligned with v is the stability axis, is the wind axis. So which one is it? Which one is it? Which is aligned to the v axis? Okay, sorry about that. I didn't realize the mic was turned off. Okay, so anything aligned with the velocity vector v is the wind axis, and the wind axis is the stability axis. Correct? So which one is aligned to the velocity vector? Which axis system is aligned to the velocity vector? In this case, in this figure. Which one is aligned to the velocity vector v? The x dash. Okay, so what other vectors go with x dash? So see, this is the velocity vector, so that is the x dash, and when you rotate zb with this alpha, you have this z dash, and z with the alpha angle, so y remains the same. So what is the stability axis? X dash, y dash, z dash. Is this clear? Is there any doubt? Is this clear? Anything aligned with the velocity axis is the stability axis, right? So it is x dash, z dash, y dash. Okay, now let's go to the next question. Let u, v, w be the velocity components in the stability axis. In our case, it is x dash, y dash, z dash. Then which of the following statements is correct? Just see carefully, look at the question carefully and answer. So if it's aligned to the velocity vector is it's v. Now if it is aligned to the velocity vector, will it have components in other directions? So in this x dash direction, it's taking some time to load. Okay, yeah. In the x dash direction, that is u, will not be 0 because it is aligned to that. So in y dash direction, z dash direction, what will be the components? Will it have components? Will it have components? No, right? Because the velocity vector is aligned to the x dash. So there won't be other components in the z and y directions, right? So your final answer is u not equal to 0, v equal to 0, w equal to 0. Correct? Okay. Now let's look at the longitudinal dynamic stability. So we take just the three equations, right? Just the three equations of motion. That takes u dot, w dot and q dot. Okay. So it is the motion in the longitudinal axis, the translational and the rotational. Okay. So you have these three equations of motion and let's analyze this. How do we analyze this? We take something known as a small perturbation theory. What do we do there? We perturb the body at equilibrium. For an aircraft in equilibrium, what is the aircraft in equilibrium? The steady state equations. What is such a condition that we've seen? Aircraft in equilibrium is also called what was the one condition? What is the aircraft in equilibrium called? Trim, right? Okay, so take any such equilibrium conditions, steady state equations, and perturb the aircraft at such a condition. So the values at equilibrium are written with the subscript 1. So this u1, v1, p1, theta 1, fay1, actually even moment. So you have moment a or moment x is moment x1 plus m, so on and so forth. Okay, so you have all quantities at steady state plus a small perturbation, that is small u. All the small letters are the small perturbations. Now the equations of motions are written with respect to these new variables. Okay, and like we had mentioned before, in order to simplify the analysis, we take stability axis. What is stability axis? It is chosen along the velocity vector. Okay, greatly simplifies the equations because many quantities are measured in the direction of a velocity or perpendicular to it, like lift, drag, all of them are measured with respect to these relative velocity parameters. So they greatly simplify our equations. So the simplified three equations for the longitudinal dynamic stability analysis are given here. Okay, okay. Now let's move on. Just a minute. Okay. Now we expand each of those three terms, that is fx, fz and m. Okay, we expand each of these three terms, take their derivatives with respect to u, alpha, delta e, q and alpha dot. Okay, so in the x direction, though there are quantities pertaining to q and alpha dot, they are negligible, hence can be ignored. Okay, but in the z direction, and the m, they cannot be ignored. Alright, so these are the equations along with the stability derivatives, and each of these derivatives have been derived in the classes. So I've just summarized them here. Let's have a look. So dou fx a by dou u u1. So they are just two non-dimensionalized. Okay, so this u by u1, again someone had asked in the forum, I think, why is it divided by u1? That is how we are defining. Okay, so we are defining it such that we can non-dimensionalize that parameter. Okay, so that is why we are dividing it by u1. That is how we are defining this equation. Okay, so that you can see in all three cases. So you have that dou u by u1. Okay, now so these three derivatives are given by these three equations, and upon substituting these terms you get the final equation of motion in this form, and we write it in a compact form in this way. Okay, where xu, this capital xu, x alpha, x delta e are given by those derivatives, those parameters. Okay, so they're just written in a compact form. So this is xu, this is x alpha, and you have that minus g theta cos theta 1. Okay, so remember that the quantities with subscript 1 are the steady state or the equilibrium values, trim values. Okay, now we look at the next set of equations and its derivatives. In this case you have terms pertaining to alpha dot and q, because they are not negligible here. So when we had first introduced this alpha dot, I had asked you why alpha dot. The two reasons are given here. Okay, why there is an alpha dot, why do you have a rate of change of alpha dot? Because as soon as you give the change, give the command, it does not achieve that alpha value, right? So you want it to fly at some alpha, for that you introduce the pitch, but it does not attain that alpha immediately. It attains the alpha over a period of time. Okay, so there is a build-up of lift over a period of time to attain this alpha. So there is a rate of change of alpha. Then another parameter that contributes is the downwash. What was downwash? Can someone tell me? We had discussed this extensively in this series. So what is downwash? What is downwash? I think we'd seen graphically also, we discussed this extensively. What is downwash? What is downwash? We'd even seen the downwash angle, its effects on the pitching moment coefficient and all of that. What is downwash? What is downwash? Downwash angle. Can you see any notation here, any term here that reminds you of downwash angle? this epsilon here, this epsilon, does it remind you of something? What was downwash? I'm not going to explain downwash again. Wingtip vortices, do all of these ring any bells? You had epsilon is epsilon naught plus dou epsilon by dou alpha into alpha. Do you remember this equation? Do you remember this equation? Okay, can you quickly Google and tell me what is downwash? Just give me one line. Okay, I don't think I'll explain downwash again. We've done this multiple times. Okay, so because of this downwash and because of the time it takes to achieve the angle of attack, you have this alpha dot. Okay, so that is why you have this rate of change of angle of attack. Not just the pitch rate, but also the rate of change of angle of attack. Now these parameters also contribute towards the derivatives in the z and the z equation, fz equation, and so you have two new terms. And here, do not get confused with this minus sign. It's just that it is in the negative z direction. It comes in the upward direction. Okay, so the lift acts upward, and that will be in the opposite z direction. ZB of the body frame, z axis of the body frame is in the vertical downward direction, right? So your lift is acting in the opposite direction, which is why this negative quantity comes. Okay, do not get confused. Okay, so now similar to the previous case, you have the final equations of motion here simplified and substituted with the parameters, and then you have for the pitch rate q dot equation. Okay, here also the terms alpha, again it's taking time to load. Yeah, so you have alpha dot and q here also. Alright, so you have these two new terms here also. Again, the alpha dot comes due to this downwash. Downwash is something that you will go back and refer to your notes and find out. Alright, okay, so these are the three final equations of motion. Which three? This u dot, this w dot, and this q dot. Okay, okay, now let's look at some of the questions. Given y double dash minus 5y dash plus 6y equal to 0 and the two initial conditions, what will be the value of yt? Okay, it's taking time to load. Alright, yeah, so this is the question. So basically they've asked you how to solve this equation. It's a simple ODE. How do you solve this? How do you go about solving this? If you recall from your maths classes, how do you go about solving this? I'll give you maybe couple of minutes to solve this and then we'll solve it. I think it's similar to your assignment question, so it will be helpful. I think you've already solved these assignments, so it should be simple for you. I'll give you a couple of minutes, then we'll solve it. It's a simple ODE, okay? You can just solve it and then find out the coefficients or the constants of integration using the initial conditions. Okay, let's solve this now. Okay, so what you do, you take let y of t equal e power 80. Okay, so let's just take it this way. Now substitute this value of y into this differential equation and try to solve it. How do you do it? If you substitute it into the differential equation, you get your characteristic equation. What do you get the equation as? You get what do you get? A square minus 5a plus 6 equal to 0. This is your characteristic equation. Now what are the roots of this equation? How do you find the roots? You get, so let's try solving this. This is a minus 3 and a plus, okay, minus 2 equal to 0. So the roots are 2 comma 3. And what is the solution? That y is equal to c1 e power a_t a1t plus c2 e power a2t. That is c1 e power 2t plus c2 e power 3t. So straight away you can eliminate two options. So it's not this, it's not this, it's one of the last two. Now using your initial conditions, find out c1, c2. I hope you've solved it. Can you tell me what is c1, c2? Can you tell me what are the c1, c2 constants? Just substitute the initial conditions, y0 and y dash, to find out c1, c2. You get two equations, two variables, c1, c2, and you can find out. Okay, so you get c1 as 4 and c2 as minus 2. So the final answer is this one. Right? Okay. Let's go to the next question. Okay, again there is a slight delay. Okay. For the system shown below, find the value of the damping ratio. How do you do this? So we know this standard second order equation. So what is the equation? You have s square plus 2 eta omega n s plus omega n square equal to 0, right? So now if you equate the denominator and this equation, will you be able to find out the damping ratio? You should be able to do it, right? Try doing it. Try doing it. Just equate the two terms. So you have s square plus 8s plus 20. Okay, let's write it neatly. S square plus 8s plus 20 is equal to s square plus 2 eta omega ns plus omega n square equal to 0. So you have omega n square equal to 20 and 2 eta omega n equal to 8. So from these two equations, can you find out eta? What is the value of eta? So from this you have omega n is root 20, and here you will have eta is 8 by 2 root 20. So what is eta? What is the value of eta? 0.894. Correct me if I am wrong, okay? I gave you a couple of minutes to solve and correct me if I am wrong. Okay, let's go to the next question. For the system shown in the figure, what is the time response for step input? Okay, okay, it has a lag. Yeah, so look at this equation, look at the denominator equation. One simple way that I can tell you is find out eta. Find out eta like you did in the previous case for any such equation where the graph is given, you find out eta and try comparing it. So if eta is greater than 1, it is overdamped, right? If eta is less than 1, it's underdamped. And then you have critically damped, okay? So find out the eta in this case. Tell me what is the eta. Just tell me if it's greater than 1, less than 1, equal to 1. Here eta is 1.5, right? So it's greater than 1. So it is overdamped. So is it this or this from the nature of the graph? Can you tell me? Also look at the equation. So they're giving you the final value, right? So they're giving you CT. CT is the output equation, C of t. Can you just look at the equation of these two graphs and try to tell me which is critically damped, which is overdamped? There is a method to find out the exact equation of this, the GS. We'll get into that in a while, but just this is a simple way. If the graphs are given to you, you will be able to find out quickly. So critically damped is this straight response, and then for your overdamped case, it's slightly below that, correct? Which is what is given in this graph. So this is the right answer. Okay, option A is the right answer. But okay, I put 2 ticks. Just give me a minute. I'll just write this neatly. Okay. So from our damping ratio, we know it's either this or this. Now the overdamped and critically damped, if you just compare the two graphs, it's something like this, right? So for our overdamped case, this is the right value, right graph. Okay, so how do you find out the solution directly? This is from the value of the damping ratio. How do you find out the solution directly? How do you do it? So this is something that I want you to try it by yourself and let me know in the next class. But if you've given the graphs, you just try to find out the damping ratio and then try to find out the answer. Okay, so let's look at another question. Look at this one. So the equation has changed. Equation has changed. Yeah. Now tell me which one would be the right graph. So the first case was overdamped. Now find the damping ratio again. What is the damping ratio here in this case? What is the damping ratio here? Damping ratio is 1. So when I'd asked you to look at, so this is critically damped. Okay, so this is the right answer. When I'd asked you to look at the equations for critically damped and over damped, so this equation and this, look at the nature of the equation. Here you have 3t e power minus 3t and e power minus 3t. That means you have repeated roots. So if your damping ratio is 1, you will have repeated roots, right? So you know that this is critically damped. This is critically damped and this is over damped. Over damped. This is critical. Sorry. 1 second. This is the right answer, and this is critically damped and this is over damped. Here you have repeated roots. Okay, just look at that. So that is another one technique you can use if the equations are given. If the graph is given, you can just find out eta and try to find out. If the equations are given, you can use this another technique. Otherwise, you can solve the equations to find out, which I think you should let me know in the next class. Just try solving it and tell me. Okay, now final example. So the equation has changed here. Now what is the value of eta? It should be very simple. What is the value of eta? Eta is 0. Correct? So now which one will be the graph? When eta is 0, what does it mean? It's undamped. When the damping ratio is 0, it means it's undamped. So which of these graphs shows you undamped nature? This one, right? So it is not damping at all. It's continuing with the same amplitude. It's continuing oscillations with the same amplitude. Correct? This again you will be able to solve using analytical method, but these are the simple methods. Okay? Okay, I think with this we will end the session today. Does anybody have any doubts? Just try solving these 3 questions analytically. We will discuss them in the next lecture. Okay, if nobody has any questions, we'll end the session here. We'll meet on Tuesday. Okay, so thank you. Good luck studying the lectures. We'll meet on Tuesday.